Let's take a look at work, energy, and power. How do forces transfer energy to or from a system? In this lesson, we're going to be able to explain how a force transfers energy through a process called work, calculate the amount of work performed by a force, state the energy transfer that takes place when a force performs work, and then we'll talk about the rate that work is done. All right, so work is energy given to or taken from a system by a force. Symbol capital W. Units are joules. The basic equation is work equals force times displacement times cosine of the angle. Just so you know, if I were to write on the screen when I talk about work, I do use capital W, but my handwriting's not that great, so what's the difference between these two? So what I do is I give little wings to the W, just so you know that's a capital, and then that's a lowercase. So this I may use if I'm talking about weight, whereas this I would use to talk about work. Power is the rate at which energy is transformed. Symbol capital P. The units are the watt. And the basic equation is power is the change in energy over time. Mechanical energy is the sum total of a system's kinetic energies and potential energies. So chemical, thermal, sound, and light energies are not part of mechanical energy. Only kinetic energy and potential energy. Conservative force. A force that conserves mechanical energy. Changes kinetic energy into potential energy and vice versa. A non-conservative force is a force that changes kinetic energy into dissipated energy, which we learned about last lesson. Work is a transfer of energy. Force has two jobs. When a force acts on an object, the force can make two transfers. When a force transfers energy, this process is called work. A force can also transfer momentum, which we'll look at later. This transfer of momentum is called impulse. One force can perform both transfers at the same time. Right now, we're only concentrating on work, which is the transfer of energy. Remember, energy and momentum are different, separate quantities that are conserved separately. Misconception says work is measured in joules, then work must be another form of energy, like kinetic energy, or potential energy, or thermal energy, or chemical energy. No, that is not correct. Work is the transfer of energy from one object or system to another. Work is not something an object has, or gains, or loses. Work is the gain or loss of energy by transfer. Work is measured in joules just like all forms of energy, but work is not a form of energy. Because energy is conserved, if an object or system gains energy, then the energy was transferred to the object or system. Likewise, if an object or system loses energy, then the energy was transferred away from the object or system to something else. If I have energy, if I get energy, then that energy came from somewhere. If I lose energy, that energy has to go somewhere. When a force is responsible for this transfer, then the amount of energy transferred is the work. So work is not energy, but work is the amount of energy that is transferred. A force does not always do work. For a force to do work, there you go. For a force to do work, the force must act while the object is moving. Has to undergo a displacement. Has to act in a direction that is not perpendicular to the displacement of the object. If a force does not change with time, the equation that calculates work is work equals force times displacement times cosine of the angle. F is the force doing the work. The displacement's length, or the distance, is d. The angle between the force vector and the displacement vector is theta. A little math break here. So this is called a scalar dot product that you'll learn about at some point in math. I don't know what math class, but there's a dot here when you have these two vectors and you multiply them and you only look at the parallel component between these two, then what you're going to end up with is a scalar. So this is a vector, and we end up with a scalar. This cosine angle. If a force does not change, isn't that kind of a weird thing to say? It is. When we get to the calculus, we can deal with a force that changes. The equation is just the integral of your force with respect to your displacement, in which case we use r. We'll deal with that when we deal with calculus. All right, so considering this situation where the boy pulls his sister in the sled, right now we will only consider the tension force acting on the sled because the up and the downs cancel out. Okay. So we have the tension force, which is at an angle. It's neither parallel nor perpendicular to our acceleration. To calculate the work done by the boy on the sled, plug the number of newtons of the tension force, number of meters of the displacement, and the angle between the two vectors into work equals force times displacement cosine theta. The amount of work is how much energy the boy loses. He burns calories pulling the rope. And how much energy is gained by the sled-sister system as the sled and the sister try to speed up due to the tension force. If a force makes an oblique angle to displacement, oblique, obtuse angle, same thing. The force is not parallel or perpendicular to displacement. Then the force has two components. One component is perpendicular to displacement, called the force perpendicular, labeled F sub perpendicular symbol, looks like an upside down T. This component does zero work, does no work. The other component is the parallel to displacement and is called force parallel, F sub this parallel symbol. This is the component that will do the work. After resolving a force into parallel and perpendicular components, the work done can more easily be calculated using W equals the parallel force to displacement. So when we resolve this into components, we have the perpendicular component and the parallel component. Notice how the parallel component is parallel to the displacement. That means this piece of the triangle, this adjacent side of the triangle, is what we would multiply the distance by. This side of the triangle, the opposite side of the triangle, would be the perpendicular, ft sine theta. And what's sine of 90? 0. So this component over here is 90 degrees in relative to the displacement. So sine of 90 is 0, so the perpendicular component is 0, no work. The other component is the adjacent, so we would use cosine, and that is ft cosine theta. Cosine of 0, because they're in the same direction, so cosine of 0 is 1. Calculating the work using F parallel D after calculating F parallel equals ft cosine theta. Or we can use ft times d cosine to calculate the work. Either way, we have to use the cosine function because the force makes an angle with the displacement. Two different ways there that we covered. You can just use the tension force times distance and then multiply that by cosine theta, or you can look at just the parallel component.